Hello everyone, welcome to today's live broadcast, HILIC, Practical Tips and Guidance for Method Development. I'm Kate Mossford, the Managing Editor of LCGC Europe, and I'll be your moderator for today's event. We are pleased to bring you this web seminar presented by LCGC and sponsored by MacMod. A company should be able to condense its mission statement into a simple phrase. MacMod's mission statement is smarter chromatography. But you may ask, what does smarter chromatography mean? It means that when they make a recommendation to you about an HPLC or UHPLC product, it is to partner with you to offer innovative solutions to your complex problems. They use advanced state-of-the-art analytical software to match their product portfolio with your separation needs. They leverage their 30-plus years of experience in the LC column business, their technical expertise and manufacturing network to help you solve your toughest application problems. MacMod provides up-to-date and accurate technical catalogues and reports from industry-leading separation scientists to keep you informed of new technologies. To learn more, please visit them on the web at www.mac-mod.com. We have a few important announcements before we begin. This webcast is designed to be interactive, and we encourage you to ask questions during the event. You can submit questions by typing them in the Q&A box, which can be found on the right-hand side of your screen. You can enlarge the slide window by clicking on the small green icon in the upper right-hand corner of the window, or by hovering your mouse over the lower right-hand corner and dragging the window to the required size. The slides will advance automatically during the event. If you have any technical problems viewing or hearing this presentation, please click on the question mark help widget in the dock at the bottom of your presentation window. I would now like to introduce today's speaker. We are pleased to be joined today by Dr. Annette Larder. Dr. Annette Larder has over 20 years of experience working in the HICROM technical support team, offering advice to chromatographers in all disciplines. Key support areas of expertise include troubleshooting, method development and optimization strategies, and column selection. Annette has been invited to deliver HPLC technical seminars in Europe and Asia at both conferences and at customer sites. Annette has hands-on experience in the manufacturing of HPLC columns. Thank you for joining us today. Please get us started.
Thank you very much indeed for that very kind introduction. I'm very grateful for the opportunity to present today and thank everybody who has signed in to listen to the presentation. So it is about HILIC. It's about hydrophilic interaction liquid chromatography. And HILIC separations we see are certainly gaining popularity in many industry sectors and application areas. However, we believe that HILIC method development experience in particular is still very low compared to our experience with reverse phase. And there are many misnomers associated with HILIC. So I hope that the following seminar, with its reviews of the basic principles of HILIC, and we look at hints and tips and tricks, which are well supported with data and examples that we have generated in our lab, will assist you in considering HILIC or your methods for your current or future separations. And for those of you who have maybe experienced some hiccups with HILIC in the past, you may look to explore HILIC once more. The seminar, the presentation is split into two parts. So in the first part, we will review the basics of HILIC, what it is and when it should be used. Now, as separation scientists, we are challenged, for some of us, pretty much every day, to separate different analytes in different matrices. So we need to look and see when we can consider HILIC to be more appropriate than some of the modes of chromatography that we are generally more used to. Certainly reverse phase, for example, ion exchange, perhaps even ion pair reverse phase, normal phase, or maybe even GC. We will then look at the advantages of HILIC, and we do importantly recognize some of the disadvantages of HILIC. And the latter, I would say, with the advantages, have certainly led to some discourse and frustration from chromatographers. But hopefully when these advantages are better understood, you will see results improving. I shall talk about different types of HILIC phases that are available. Again, speaking to many of our customers, it's interesting to know that many are unaware that different HILIC phases are indeed available. We are going to look in detail at the HILIC mobile phases and their effect on successful HILIC separations. Then a variety of hints and tips, two key ones, column equilibration and sample diluent. Both of these, I'll tell you already, are quite different to the familiar reverse phase approach. The second part of the presentation is we remind ourselves of the importance of selectivity in chromatography and certainly with method development. We will look at a very simple method development approach, obviously with HILIC, and we will look to separate using our flow of our method development at caffeine and simulated compounds. So what is HILIC? Well, I will continue to use HILIC because hydrophilic interaction liquid chromatography is a little too long. So HILIC was introduced as a concept by Andrew Alpert. And whilst HILIC actually uses some similar elements to reverse phase, HILIC provides a suitable retention and separation for hydrophilic, or let's call them polar and very polar analytes, which fail to retain in many reverse phase situations. Now, it's the aqueous component of the mobile phase that allows a hydrophilic environment to exist around what we typically use as a polar stationary phase. And we effectively get the formation of an absorbed water layer around the silica particle. And it's in this water layer that analytes partition. We have a partitioning mechanism. Now, this water layer is very important for HILIC. We have to develop it, and then we need to maintain it through our HILIC analysis. Now, analytes, as I say, can work by partitioning in this aqueous phase, but there are actually various other polar interaction mechanisms, such as electrostatic, such as ion exchange, and hydrogen bonding that can occur too. So polar analytes will use all or some of these mechanisms for their retention. So HILIC is perhaps considered to be a more complex technique as it has multiple modes of interactions. Now, the weightings of all these different interactions are based on a combination of the stationary phase that we use, the mobile phase and the pH of that, and certainly with the physical chemical properties of the analytes. So it's safe to say HILIC is a multimodal interaction technique, but ultimately these interactions will help us with the retention and the separation of our challenging polar compounds that we find to be challenging because they don't retain so well under our familiar reverse phase conditions. In terms of the mobile phases, as I said, we tend to use similar elements to reverse phase, but with HILIC, in HILIC, the strengths of our phases are actually different. In HILIC, water is the strong solvent, okay? So to decrease retention, we would increase polarity of the mobile phase, and in HILIC, we do so by increasing water. The bulk solvent in HILIC, however, is acetonitrile. Acetonitrile, this is an aprotic solvent. It is essential, however, that we maintain approximately 3% minimum of our aqueous proportion. in order that we maintain that hydration, that water layer around the particles, certainly for the main part of the partitioning mechanism. Now, other organic solvents can be used, as obviously as you know, in reverse phase. We tend to use acetonitrile and possibly otherwise methanol. The methanol is a protic solvent. So if we were to use that as the bulk solvent in HILIC, it may disrupt the water layer because it will hydrogen bond, and this will lead to reduced retention and repeatability. It is plausible, we've seen in many circumstances where a very small percentage of methanol is used, maybe 1 to 2%, added to the mobile phase. It can aid selectivity and may also aid solubility. So when should we use, as a chromatographer, when should we use HILIC? Are there any ways in which we can make some informed decisions? Well, the first one is if we know the analyte structure and the log P values. As I'm sure you know, the log P values are indicators of lack of phylicity, or you could look at it conversely as hydrophilicity. And there's a rule of thumb, as we'll see from the log P scale that I've now introduced to this slide. We have a log P scale from -5 through 0 to +5. So we've got log P0 at the center. And we've added on 3 model compounds. Glyphosate, for those of you who are agrochemical, will know that glyphosate is a very polar agrocompound with 3 polar groups, and its log P is -2.39. We have caffeine of log P, which is -0.13. And then we have amitriptyline, which is our model pharmaceutical compound. It's a tricyclic antidepressant, and it's a log P of 4.9. And you'll see on the scale that we have a range of log Ps that are covered by reverse phase, typically somewhere between sort of -1.5 and +5. And then we have a range of log P that is covered by HILIC, and that's from about +1.5 down to -5. So any compounds that have a log P, certainly that are less than 0, are deemed suitable for HILIC. And we typically can use caffeine with a log P almost of 0 as effectively a reference marker. Now you will notice that there is an overlap zone here. That is from -1.5 to +1.5. Now whether you choose reverse phase or HILIC is very much dependent on the application, the analyte and the situation. So a call needs to be made there. However, what if we don't know our compounds? What if we don't know the structure and this useful log P data? Well, we can evaluate under reverse phase. And as I've mentioned before, caffeine is a good indicator. And we can use its reference as an indicator and compare that to the retention times of our other components. So what we've got here is we've got an example of these 3 columns I've already mentioned, and they're run on a C18 column. And we have a gradient from 5 to 100% in 10 minutes. So we have the glyphosate coming off at 1.2 minutes. So it's pretty much eluting near the column void. The caffeine retention time is about 6 minutes. And the amitriptyline, well, we could probably predict its retention is going to be more than caffeine, and its retention is 9.5. So our rule of thumb, if an analyte elutes before caffeine, in HILIC, then HILIC is considered to be the option. So if caffeine isn't already in your sample, then why not spike it and establish the relative retention times. So now I've introduced some basics of HILIC and suggested when we can use it. So what does HILIC offer to us, the chromatographer? Well, I've already promised you, or endeavoured to promise, that it provides retention of compounds that are hard to retain on a reverse phase system. These are typically polar neutral or polar charged species. So metabolites, polar pharmaceuticals, polar pesticides, sugars, saccharides, for example, amino acids, organic acids, phosphates, and also some phenolics that we see a lot of at the moment in food and beverage. Another second attractive characteristic of HILIC is it provides orthogonal selectivity to reverse phase. Well, what exactly do I mean by that? Well, here in the first schematic, we've got 6 compounds that we run under reverse phase conditions. So on the C18 column, where we have a low content, 5% of acetonitrile and 95% of water. And they've alluded in the order as we've written the compounds there, 1 through to 6. The same 6 compounds will run on a HILIC character stationary phase, so run under HILIC conditions. So we have the bulk element as acetonitrile at 95% and 5% water. And you will see we have a complete reversal of the elution order of these 6 compounds. They're now listed from 6 through to 1. So HILIC can give us quite a different selectivity profile compared to reverse phase. Now I'd like to review key advantages of using HILIC. So it's already established that it's highly suited to retention of polar to very polar analytes. We can strive to get the retention of reverse phase, but this usually involves the need for use of iron pair reagents and additives. And for those of you who have have ever used certainly iron pair reagents will know that this can be quite a challenge. The iron pairing reagents can be quite challenging in the equilibration of the column of the system, and they can be sticky. They get stuck in various on places on the system and on the column. Another advantage of HILIC is that we use a high volume fraction organic solvent eluents, and they will enhance the mass transfer and lower the C-term contribution of the all-important chromatographic Van Dientor equation. And what this means is we get better efficiency, and this ultimately leads to better chromatography. The high organic content can also aid ionization for some detection techniques such as MS and ELSD. Typically, we've seen it's not uncommon for 80 to 90% of acetonitrile to be used in HILIC separations. The high organic content is ideal for desolvation, for ion formation, and enhanced signal response, and also it lowers the surface tension. With acetonitrile being the bulk solvent, as we know very much from reverse phase, it has low viscosity, which translates into lower back pressures. So depending obviously, of course, of the initial situation, of your instrumentation, then we can use it potentially at higher flow rates. Also with a combination of smaller particle sizes, we get higher plate counts, higher efficiencies. And with gradients, of course, that equates to higher peak capacities. So as I said at the top, it is important to also recognize the disadvantages of HILIC. And principally failure and frustration that we know from our customers and chromatographers that HILIC has occurred with the failure. And it's occurred because HILIC knowledge and experience is generally at the moment far lower than for reverse phase liquid chromatography. The guidelines that we follow when we adopt and we adapt for reverse phase do need to be different for HILIC. If we try and apply them, the rules, I suppose, that we apply for reverse phase to HILIC, this will lead to poor chromatography, and we'll then explore the differences in a little bit more detail. Before I go on, I should mention that stationary phase options are less, but I will show that there are plenty of phases available to do some very good method development. Another challenge is this high volume fraction eluents that can lead to challenges with solubility for the very polar analytes, and also keeping them solubilized. So more of this later. And actually solubility can often be the primary reason why people are put off by HILIC. With regards to retention modeling, which is quite commonplace in chromatography now in developing methods, experiences with retention modeling in HILIC we've seen have been mixed. There are many observations in the published literature, and we've seen mixed reviews between success and failure. We've highlighted the top part in terms of HILIC knowledge and experience. We feel that we really wanted to address this, and hence the reason for today's presentation. So now I want to experience some sort of practical experiences with you, and the first topic is the HILIC stationary phase. There are a variety of commercially specially bonded phases for HILIC, and they're broadly classed according to their phase characteristics, whether it be acidic character, basic character, neutral, and the others, the novel phases, the weirder ones, may I dare say, the split ionic, the cyclodextrin. It is always useful to consider different stationary phases for method development, and we advocate that whether we're doing HILIC or we're doing reverse phase. It's likely that if we will duplicate results if we were to choose a stationary phase with very similar character. So, for example, in HILIC, we're using an acidic, if we were to be using an acidic character phase and we're failing to get the separation, we would likely to duplicate results by choosing another phase of acidic character. We need to look outside the possibilities of acidic. So, here we have three different types of column chemistries: an acidic phase, a basic phase, and a neutral phase here in this tabulated format. And they're all characterized depending upon some of their properties. And this type of characterization actually is quite typical and quite common in chromatography. So we have looked at the partitioning of analytes into the water layer on each of these phases. We've also looked at the anionic and analyte interactions, the cationic analyte interactions, and also hydrogen bonding. And what we want to see here in the table is effectively the different weightings between these different types of characteristic stationary phases. So it allows us to explain and try and understand how the properties of these columns and these phases and how they're designed to help with different types of separations. So what does this mean chromatographically between these different characteristic stationary phases? So this slide, we've studied the behavior of a nine-polar compound mixture containing an acid and base and neutral analytes. And we've actually run them isocratically on the three stationary phases. So the acidic, the neutral, and the basic characters. And we've run them at a pH of 4.7. And you can see already easily how different the chromatographic profiles are between them. If we pick out a neutral analyte, which we've done already, so if you follow the green line, this is a compound called 2-deoxyguanosine. And what you can simply see is the change in retention of this compound on the acidic phase compared to the basic and neutral phases. Now we pick an acidic analyte. This is 4-hydroxybenzoic acid, so denoted by these red lines. And the difference, again, in the retention is clear to see for this analyte compound on the three different stationary phases. And we take an example now of a basic compound. This is atenolol. And again, a different retention of the basic compound on these three stationary phases. Remember, these are all at 1 pH. So selectivity is different with this set of compounds with these phases. And the elution orders are written here for you to see, and they are changing on these different stationary phases. Now, this screening approach is very important for method development, and we do strongly advocate screening different character stationary phases as the first step in any method development. Very briefly, these three phases I've just been talking about, I'm sorry if it appears rather small on your screen, but what we've got here at the top is highlighted these HILIC phases. And so for those of you interested, USP listing, for example, the functionality, the surface area, etc., all that information is there on the slide, and we can share that at length with you. So now I'd like to move on and look at some HILIC eluent parameters. So the first one is eluent pH, and for those of you who know that pH is a very powerful method development tool in HILIC and also in reverse phase. Now in this example we have a 6-compound mixture. Again, we've got an acid, we've got neutral, we've got basic character analytes. Now we're running these 6 compounds just on one phase, and that's an acidic character phase. But at 3 different pHs of 3, of 4.7 and 6. And you can see clearly from the chromatographic profiles that we get differences in retention and elution order of these compounds depending on the pH. So pH is a very useful method development tool. The reason is because the pH is influencing not only the ionization state of the analyte, but also of the stationary phase as well. Now, of course, if all these compounds were polar neutrals, then pH is likely to have little or possibly no effect. We turn our attention to the effect of buffer concentration on analytes. Again, we're using an acidic stationary, HILIC acidic stationary phase for this example. And we have a mixture containing 3 compounds, and we've actually started off by highlighting compound 3, which is procainamide. It's a basic analyte. And it appears to be well retained at a low buffer concentration of 2 millimolar. But as the buffer concentration is continually increased, so as we make our way down the slide, you'll see we've got a continuing increase of the buffer concentration. And the retention time, as we increase the buffer, is changing, and it's actually decreasing in the case of this basic analyte. I should note that whilst we're changing the buffer concentration, we're keeping all other parameters the same. So what's happening here? Again, we're getting some stationary phase interactions, of course, but possibly what we're predominantly doing is we're affecting the absorbed water layer that is around our stationary phase, our silica particles. Remember, this water layer is at the center of the HILIC mechanism. So any change to the absorbed water layer is going to change any mechanisms of interaction. So as well as partitioning, it could also affect the weightings of the ion exchange, the electrostatic and hydrogen bonding, for example. Another parameter is temperature, so another key powerful tool for method development. The separation that we're looking here is actually on the neutral character stationary phase, and again, a 4-compound mixture with an acid, a base, and a neutral. And you'll see as we increase the temperature systematically from 10-degree increments, so 10 degrees for 20, 30, and upwards to 50, there is an increased retention of the compound number 4, which is tryptophan. For the remainder, we see a decrease in retention time. This is possibly more of what we would expect as we increase temperature. So clearly something different is occurring for this basic compound. Now I'd like to discuss 2 key topics on HILIC. One is column equilibration and the other is the sample diluent. In column equilibration in HILIC is really important, but it is very important whatever chromatographic mode that you use. And I think here certainly with in HILIC, where it apparently fails is there is a lack of appreciation with regard to column equilibration, and this will lead to frustration. In reverse phase, we get stable retention typically after about 10 column volumes. So we run 10 column volumes through a reverse phase situation, and we reach our steady state, as we've shown here in these graphics. Okay, referring to the reverse phase as the green line. In HILIC, however, which is the blue line here, the equilibration time or volume is much longer. It can require up to 50 to 60 column volumes on a brand new column, and I stress the brand new column, to establish a stable retention. So what we're doing here with a brand new HILIC column is establishing that stable hydration layer around the silica. And we've determined it's about 50 to 60 column volumes. We've looked at a number of different situations, different columns, and different stationary phases, and this 50 to 60 appears to be very true. However, interestingly, that when a column has been used, and we can use it for a number of injections, when we clean it, when we flush it, when we store it, and we come back to use it, the equilibration time is much less, around about 20 column volumes. For isocratic HILIC methods, once the equilibration has been established, it's complete, it is stable, so we don't need to condition it or equilibrate it between runs. However, with gradient HILIC methods, we need about approximately 10 column volumes between each gradient run to reach a steady state. Now, the time, the column volume, the equilibration time can vary depending on the phase character and the eluent and the analytes that we're using. So it can be application dependent. So we might want to explore this as a parameter almost for method development in any different situation. I just want to quickly review exactly what we mean by column volume. So we've got a couple of slides to explain this briefly. Column volume is the amount of eluent in a column that's actually occupying the space between the particles, of course, packed into a column and also within the pores. So we can sort of start with our mathematical equation for establishing the volume of a cylinder, which is pi r squared L, of course r being the radius, so we know the ID of the column, and L being the length of the column. But we also have to take into account, you'll see at the end of this equation, is the bed porosity value. And that value is going to be dependent on what silica that you've actually got or has packed into the column. And what we've just shown here is some typical values, in fact, for our ACE materials. So you'll see different porosity depending on what the pore size is of a fully porous material, and also we have the value for solid core material as well. So depending on what brand of HILIC column that you're using, you may need to either determine the porosity value experimentally for yourself or contact the manufacturer for their information. Column volume is independent of flow rate and column dimension. So it's a better term we find to use to understand equilibration. But I know that some of us, even myself, like to establish that in terms of, well, the time. What time does it take? How long will it take to equilibrate my column? So what does this basically mean practically? So in the top table, table number, the first table here, so for a number of different column dimensions, so we've got length against ID, we've actually calculated column volumes. And these are based on a porous silica of 100 angstrom. So I've just highlighted in the box here in the far right-hand corner, this is a 250 bore 4.6, and the column volume we can calculate to be 2.617 mils. So what exactly does that mean in terms of equilibration time? So in the second table in this slide, we show the time that's required at various flow rates to achieve the 20 or the 60 column volumes if it's a brand new column. For a number of different, again, these would be 100 angstrom per silica columns. So we've identified the typical flow rates that we would use these different column dimensions at. So again, we've highlighted our example of a 250 by 4.6. You can see highlighted with this strong red box here in the table. So we already know that the column volume is 2.617 mils, and at 1 mil a minute flow rate, it will require 157 minutes to achieve the 60 column volume on a brand new column to reach a steady state. Subsequent use, 20 column volumes, would require 52.3 minutes. For those of you, of course, who are perhaps using UHPLC, so you might want to use a 50 by 2.1, which we've got listed here in this table, a 1.7 micron, running it obviously at a lower, more appropriate flow rate, then you will see from a study of the information in the table that the equilibration times, of course, are going to be far less. So hopefully for some of you, this puts into context and perspective the types of columns that you are using. The second key topic after a column equilibration is sample diluent. And we know, as I mentioned before, this can be the primary decision as to whether people or chromatographers will use HILIC or not. And again, perhaps with a little bit more understanding and a little bit more assistance here, then maybe this could be re-examined. Once more, as we see with reverse phase, as we will see with HILIC, poorly optimized diluent choice can significantly reduce chromatographic performance and peak shape. And the effect of sample diluent can be different for each analyte, and also the stationary phase on which that analyte is looking to be retained. So we have some evidence already here on this first slide. This is the HILIC neutral character phase, and we've got 3 model compounds. Hypoxanthine is our neutral, tyramine our model, and we've got mandelic acid, obviously, is our model acid. And we've got different volume fractions, so using different percentages of acetonitrile in our diluent. And we use them to dissolve each analyte. And that what we wanted to do was assess the peak retention. Perhaps more importantly, what we can see on this slide is the peak shape that was attained for all of these 3 compounds. So the top left-hand corner is the hypoxanthine. So we actually get good solubility across most of the volume fractions of acetonitrile, but not when we're using 100% acetonitrile. We don't get any solubility at all. For the tyramine, we see at very low percentages of acetonitrile that we get peak splitting. We're getting peak splitting because it's an indication of a stability issue and partial solubility. So stationary phase, as I've mentioned before, can play a part. And so we see actually in the next slide where we've now gone from the neutral characteristic phase, stationary phase, and looking at these 3 compounds on the acidic character. We don't see too much change in the hypoxanthine, but we still see very poor, if no solubility with 100% acetonitrile. The tyramine would seem to have improved a little bit on peak shape, but there are still concerns at some of the lower percentages of acetonitrile. And with mandelic acid, we appear to have some actually overloading effect going on at low percentages of acetonitrile. And just to conclude the evidence, if it were needed, we're looking at the basic character HILIC column now, again with the 3 compounds. And we see very similar pattern emerging with the hypoxanthine, some severe peak issues now with the tyramine once again. And the mandelic acid seems to be, what I would say, behaving itself across the board. We recommend exploring the best diluent system. So almost doing a method development, as it were. Explore between about 20 to 80% volume fraction and increasing with 20% increments of acetonitrile. Also, I would add higher analyte concentrations and smaller injection volumes are preferable with HILIC, as we seem to suggest that they minimize disruption to the water layer. Just moving on quickly to some hints, further hints and tips when it comes to using HILIC. The first one actually is no different to when we're using reverse phase. And the essence of this slide is really to emphasize the fact that the concentration of additive in mobile phase A and mobile phase B should be the same. In this first example here, we don't have the same concentration. We've actually got a concentration of our additive as 0.4 in our A line and 5 millimolar in our B line. This is because we've prepared them as distinct volume fractions. In the second example, we've matched the buffer concentration. So here we've prepared 10 millimolar of our ammonium formate. In this particular example, pH 3, it's 10 millimolar in both of our lines. Now, if there is difference in the concentrations, this can cause us difficulties. We get an ion strength gradient, and this leads to poor retention reproducibility, stability issues in our chromatography, and what some of our customers would explain as a dancing around of peaks. So it is notable in reverse phase, and it's especially notable in HILIC, because we are disrupting that water layer once again. There are some more hints and tips, just an overview in this particular slide, but we've gone over some of them already in terms of balancing the buffer concentration. And we've discussed the need for adequate equilibration, both with a brand new column and then subsequent use of the column, reaching that steady state because we're re-establishing or generating and then re-establishing that all-important hydration layer. Don't use high water containing sample diluents, but do experiment with your sample diluent. I've already mentioned the fact that protic solvents use in your HILIC mobile phase may disrupt the water layer, and once again that will lead to robustness issues. We advocate steering away, avoiding inorganic salts, certainly things like phosphates, as they again can present solubility issues, certainly at high organic, and they again will disrupt the water layer. And we found in our particular phases that IPA is the best solvent to be using for storage, for stability and maximizing our column lifetimes. So I hope that we have pared back the issues seen perhaps by many of you in terms of using HILIC chromatography. We've addressed the pitfalls, and hopefully by providing more knowledge about HILIC, then we're going to have obviously more successful HILIC separations. We have looked at the influence already on stationary phases and also the influence of eluent pH and their effect on selectivity. We advocate screening 3 different character stationary phases at 3 different eluent pHs so that we can really maximize and look at a large selectivity space. And in so doing, that will contribute to successful and hopefully faster method development. So that moves us on now to the second part of the presentation. We'll have a quick reminder of selectivity and look at our simple method development approach to separate caffeine and cerulated compounds. So I don't perhaps need to remind you all of selectivity and its importance in the resolution, the universal resolution equation that I'm showing here on this slide. It brings together selectivity as well as efficiency and retention. So they all play their part in resolving peaks. But the graphical representation that I've shown to the right-hand side here of this slide illustrates very clearly how important selectivity is above the other parameters. And there are many experimental parameters that will, of course, affect selectivity. But whether you're using isocratic or whether you're using gradient, it is stationary phase that has the most influence on selectivity. So I said to you there would be a very simple method development approach. Obviously, method development can be very involved, and we might all have different ways in which to approach method development. So our step one, we assess our analytes. If there are any structural, chemical, physical properties that we know, log P, for example, would be very useful. From this information, it will hopefully guide us. We might be able to make a good evaluation of the stationary phase and the mobile phase that we want to use. We may need to run them, or reverse phase, spiking with caffeine, to elucidate if a HILIC method is required. Our step two is to run the Gaussian runs that I've already suggested. The 3 different pHs, 3 different stationary phases, and 1 gradient run. Hopefully we can let all our LC instrument do the work. We can then come back, assess all the information. We're assessing it for the peaks, that they have been retained, looking at the peak shape perhaps, remembering about sample diluent issues, separation and selectivity, and hopefully one of the runs has given us some real promise. The one that has given us real promise, we can move to step 3 to optimize, perhaps some tweaking. Are we going to stick with a gradient or maybe simplify with an isocratic? Do we need to modify the percentage of organic? Look at changing the buffer concentration, temperature, maybe particle size to get more efficiency, changing the column dimensions, and so on. Depending on your industry, we would validate the method according to all the correct protocols and transfer and implement. Only method development was as simple as all that. Just as a small aside, we've developed our protocol that I'm going to go through actually into a nice simplistic flow chart. It's available on an A2 poster, and if you'd like a copy of it, then do please approach us. So in the latter part now of the seminar, we're just going to look at a protocol that we've developed, a HILIC one, obviously, method development one, to separate a caffeine and some related compounds. These compounds happen to be well-established ones, so we have structural information, and we also have the log P information as well. And now, since all the log P values are less than 0, this makes them, we will predict very good candidates for HILIC. Remember, anything that has a log P less than caffeine is going to be good HILIC candidates. So they possess reasonable hydrophilicity. Can we be absolutely sure of this? So if we have the opportunity, then let's run them under reverse phase. So these compounds were done, we did exactly that. We ran them on a C18 column on a generic gradient. And remember, we're looking to see if any of them elute before caffeine. Well, in fact, all 4 of the related substances do. One, the peak there, the main peak one, is our caffeine. And in fact, 2 of them, compounds 4 and 5, have very low retention factors indeed, and in fact are unresolved. So it proves to us what we've considered, that HILIC might certainly here be a suitable alternative for reverse phase. So as I've mentioned already, for method development purposes, we recommend assessing the analytes on different stationary phases, 3 ideally, and at 3 different pHs. But we need to, of course, assess the analytes that we've got. Now, in this case, they are all polar neutrals. So we assessed that perhaps we didn't need to run at pH 6. So we're just going to run at pH 7, at pH 3 and 4.7 only. There seems to be little advantage at running at pH 7. So added to that, though the pH may not have any significant bearing on the analytes, they may of course do on the stationary phases. Because we know that any change in ionization of the stationary phase can potentially affect the hydration layer around the silica phase and the particles. So of course we may get some different leverages and weightings of the different mechanisms of interaction. In this case, we also established that we needed 80 column volumes to get a steady state on these brand new columns, and just to highlight the fact that we're running at pH 3 and 4.7. So on this next slide, here we have the gradient screening chromatographic results on all three phases at the pH of 3. And so we see the separation and behavior of all 5 analytes. The principal component 1 is the caffeine and the related substances. And we can compare those results at pH 3 with those that we've got at pH 4.7. And we do see some selectivity differences. So we're getting some options that we can choose from. Hopefully one of them we consider that we can use and develop a foolproof method. And the most promising separation in this case was on the HILIC, the neutral character phase, and at the pH of 3. So this is one we selected and we're taking forward for further optimization. So our first consideration is, do we stick with gradient or maybe simplify for isocratic? And the retention window for the early eluters is very narrow on the gradient, so it kind of suggested that maybe isocratic HILIC could be used. But we've ran at a 94% acetonitrile on isocratic, as you can see on the right-hand side, the chromatographic profile. And we actually get worse separation for our critical pairs, our peaks of 2 and 3. And we get a substantial amount of band broadening. So we're barely getting any resolution and very long retention times of our compounds of 4 and 5. And in fact, using a higher content of acetonitrile did not improve the situation under the isocratic conditions. So in this particular situation, we elected to stick with the gradient screen. We then went on to consider, well, what effect temperature might have. In fact, reducing the temperature from 25 degrees to 15 degrees, you'll see here, increased the resolution between the critical pairs of 2 and 3. In fact, to acceptable limits for this separation, we were actually doing this work on behalf of a customer, so they were very pleased with the separation that we achieved for the compounds 2 and 3, and we were still getting good baseline separation between compounds 4 and 5. So this is actually now our final method. And as I said, it was established for a customer. It was deemed to be fit for purpose for them. The principal components, so the caffeine, peak 1, sufficiently separated from the related substances. We do almost have baseline separation of peaks 2 and 3, but we can do some good integration by dropping the perpendicular between those peaks. And we've got good baseline resolution for our peaks 4 and 5. So fit for purpose, it certainly was in this case. There are just 3 slides here, but we have a lot of technical information with regard to HILIC. We have a 39-page guide, so these are all the hints and the tips and the tricks, the pros and the cons, the column equilibration, the sample diluents, everything that you might need to know about HILIC. It is generic information for any HILIC chromatography. So if you'd like a copy of this, it's free of charge. We'd be very, very keen to give you a copy. Similarly, we have some technical notes, again, focusing in on some of the key areas of column equilibration, the method development approach, and sample diluents. Again, please do approach us if you'd like copies of these free knowledge notes. They're just, I think all of them just double-sided A4. And as I've mentioned before, we have an A2 rule chart that we'd be happy to provide you with. So the penultimate slide is our summary of the presentation, and I trust that you have found the information presented in this webinar will be of use to you. We consider HILIC for our very polar analytes that we are near impossible to retain by reverse phase, and it offers alternative to selectivity to our well-known reverse phase chromatography. Many chromatographic modes can be considered to be mechanistically complex. HILIC is certainly one of those. With HILIC, we always need to consider the absorbed water layer, establishing it and maintaining it and doing our best not to disrupt it, as it will give us reproducibility issues. We've run through a simplistic screening protocol. Whatever method development protocol you have, consider selectivity at all times. It's a key parameter with chromatography. And we've looked at the impact of different stationary phases on selectivity. We've looked at some detail about the equilibration time and the sample diluent, so always keep this in mind for HILIC. We want to keep good peak shape, ideally at all times. And that brings me to the final slide, and to thank you all very much indeed for your attention. And I'd like to hand back to Kate.
Thank you, Annette, for that informative presentation. Before we get started on the question and answer session, we're going to take two brief polling questions. Please click and enter your answers directly on the screen. Here is the first question. Would you be interested in a personal consultation on your method development of your HILIC method utilizing the new HILIC 3 column protocol? Yes, no. Once again, would you be interested in a personal consultation on your method development of your HILIC method utilizing the new HILIC 3 column protocol? Yes, no. Thank you for participating in our first poll. I'd now like to ask our audience to participate in our second polling question. Please click and enter your answers directly on the screen. Here is the next question. Which manufacturer do you currently source your HILIC columns from? Waters, Agilent, Phenomenex, Toso Bioscience, Merck Millipore, Thermo Fisher Scientific, MacMod Analytical. Once again, which manufacturer do you currently source your HILIC columns from? Waters, Agilent, Phenomenex, Toso Bioscience, Merck Millipore, Thermo Fisher Scientific, MacMod Analytical. Thank you for participating in our second poll. Before we get started on the question and answer session, I would like to remind our audience how to submit questions. You can submit questions by typing them in the Q&A box, which can be found on the right-hand side of the presentation window. We'll try to answer as many questions as we can. And our first question is it possible to develop a HILIC method on an RP phase?
Thank you very much indeed for the question. So, can we develop a HILIC method on a reverse phase? I don't see why not, of course, but bearing in mind from what we've seen that we would expect a reversal, of course, of evolution on reverse phase generally. So obviously that is something that you would need to consider. In any chromatographic situation, the goal of a chromatographer is, or one chromatographer is quite different to another. So it really very much depends on whether you want polar analytes to elute first, or obviously the less polar. So that would be a consideration. So in answer to the question, yes, it's quite plausible.
Okay, thank you, Annette. Next question. The response in HILIC, is it lower than RP?
The response, I'm not entirely sure what is meant by that. Maybe that's something we can ask of the person that's offered that question. I don't know if that means in terms of peak signal perhaps or sensitivity. But again, depending on the chromatographic parameters, then there's no reason why the response should be any more or any less in HILIC than it is in reverse phase. Obviously, you've got considerations, of course, of your analytes and the concentration of those. So I hope that offers some explanation.
Thank you. And next question. How long is a HILIC column able to sit in mobile phase?
Thank you. That's another good question. We advocate for any column, and I think I can speak for any column manufacturer. You know, depending on what the column is obviously used in, if it's certainly used with any additives, I'm pairing reagent, obviously it's reverse phase, so any additives, they can certainly be used practically, obviously when the mobile phase is flowing through the column, but we would always recommend to remove any additives, so cleaning the column of additives and putting it on the solvent that is recommended by the manufacturer. We would never advocate storing with additives, certainly not in acidic or basic conditions. So abide by the guidelines for the manufacturer in terms of the storage of the column. As I mentioned before, for our columns we found it is IPA. It is the most suitable storage solvent. I hope that addresses that question.
Thank you. Next question. Is it possible to develop a single HILIC method for a mixture of acidic, basic, and neutral analytes?
Oh, absolutely, and I hope from all the examples that I've shown you, then that is absolutely achievable. Again, going through the scouting sort of process, you know, looking at different pHs. Of course, we saw, you know, will influence the elution order and behavior of the different types of analytes. So again, it comes down to the goal of the chromatographer. What would they like to see? Would it be the acid eluting first, or the neutral, or the basic compound? So yes, it is possible.
Okay, thank you, Annette. Unfortunately, we are now out of time. I would like to thank the audience for attending and for participating in today's event. I would also like to thank our sponsor, MacMod, for making today's educational webcast possible. You will receive an email from LCGC alerting you when this webcast will be available for replay. We invite you to forward that announcement to your colleagues who may have missed today's live event. Thanks for joining. We'll see you next time. Goodbye.